Alright, so in my last video, I did these first two objectives for this section. This is section 3 of chapter 9, over limiting reactants and percent yields. So we figured out that limiting reactant part of the section. We just have to deal with the theoretical yield, actual yield, percent yield at the end. So you should already have all this stuff filled in. But we still need to do this part of the notes. Okay, theoretical yield is the maximum amount of products that can be produced from given amounts of reactants, excuse me. Theoretical yield has been what we've been doing this whole time. From section 1 when we were doing ideal stoichiometry. In theory, you can make a certain amount given a certain amount of something else, always, right? Actual yield is a little bit different. We know that when reactions happen in real life, that they don't always go through to completion. If they did, when you burn that log in your fireplace, there'd be nothing left. There'd be no ash left behind because all of that carbon-containing piece of wood would have been turned into carbon dioxide and water. There'd be no products besides that. So we know that reactions don't go through to completion, but we can figure out how far through to completion it can do. That would be my percent yield. So percent yield, in order to calculate that, you actually need to take your actual divided by your theoretical and multiply times 100. I believe that's already on your notes, but I need it up here to see it. Right, there's another way that I can write this though that might actually be more useful for some of us. It can be easier to set it up like this. You can do the percent over 100 is equal to actual over theoretical. This version might be more useful for those of you that like to do a fish method to solve these problems. So I really don't care which way you do it. You can do algebra either way and get an answer, but one or the other, make sure you have that equation, but also know how to use it. So you're going to have problems like this in the future to deal with. So chlorobenzene, C6H5Cl, is used in the production of many important chemicals such as aspirin dyes, disinfectants, lots of things. One industrial method of preparing chlorobenzene is to react benzene, C6H6, with chlorine as represented by the following equation. So again, made this easy for us. Pretty sure this is a 1 to 1 to 1 to 1, right? There's no balancing involved. But the question asks, when 36.8 grams of benzene react with an excess of chlorine gas, the actual yield of chlorobenzene is 38.8 grams. What is the percent yield of chlorobenzene in this case then? So try not to get confused here. You are given a couple different values, but this 38 grams is your benzene. That's this stuff. The 38.8 grams is your chlorobenzene, which is this stuff. They're not the same thing. So I can't just use those 2 gram values that are given and try and get a percent yield. I need to have 2 different gram values for chlorobenzene to do a percent yield. So the actual yield that was given there, we're going to use that, but we need to figure out what the theoretical yield for benzene would be. We need to figure out how much chlorobenzene we could make starting from 36.8 grams of benzene. So this is actually fairly simple. We're going to do the same thing that we did in section 1. I have to find my calculator here so I can do this work. But we're going to start out, with 36.8 grams of benzene, C6H6. Remember, I can't use grams, I need moles. So 1 mole should have a certain amount of grams in it, 12.6 0.01 times 6 plus 6.06. 6 carbons, 6 hydrogens. That benzene should have a mass something like this, 78.12 grams. So that gets me from grams to moles. But I don't want benzene, I want chlorobenzene, so I need a ratio. It is 1 to 1. And that's my chlorobenzene. This is my benzene label. So I got rid of that label so I could have moles of chlorobenzene. But I don't want moles of chlorobenzene, I want grams. So I gotta basically take my 78.12, subtract one of the hydrogens, and then add a chlorine. Let me grab the periodic table here because that's one that I don't remember off the top of my head. 35.45, so I'll add that in there. And I have this mass, 112.56 grams per mole. So now it's not moles anymore, I have grams of chlorobenzene. That's what I wanted to begin with. So I multiply, divide, I can get an answer. 36.8 times 112.56, and then divide that answer by 78.12. Remember, order of operations really isn't important here. As long as you're multiplying everything on top and dividing all those things on the bottom, you should get an answer something like this. I got 53.0 grams of my chlorobenzene. And this is my theoretical yield because I'm doing my stoichiometry to get this answer. So in theory, I can make this much, but I'm probably not actually going to make that much. That's the whole point of the percent yield. So since I actually made 38.8 grams of this stuff, I'm going to take 38.8 grams of my chlorobenzene, divide that by 53, 0.0 grams. I'm going to multiply times 100, and that should give me my percent yield. So let me use my calculator here real quick. 38.8 divided by 53. I'm going to get an answer with 3 sig figs that looks like this. 0.732, oops, forgot to multiply by 100. But that makes it 73.2% as my yield. So given what I was given, when 36.8 grams of benzene react, right, in theory I could have made that 50 grams, 50 some odd grams of chlorobenzene, but in reality I only made 38.8. So I gotta divide, multiply by 100, get an answer. One thing that you'll notice when you're doing percent yields is you will, generally speaking, get a number that's below 100. Because it's not possible to actually make more than it's possible to make, right? Theoretically possible to make. So I can't actually make any more than 53 grams. So I certainly couldn't have had an actual yield of 58 grams. So these numbers, these answers are always going to be below 100. Make sure you keep that in mind. If it's not below 100, that means that there's something else in there that you're measuring instead. Going back to a previous example, I actually had a lab in college where I made aspirin. And I collected that aspirin and I weighed it to find out what my percent yield was. But it was possible for me to be over, to have over 100% for my percent yield, but that's only if I wasn't paying attention, because it's possible that there was still some water in there that I was dealing with. Right? This reaction happened in water. It also created water. I had to dry my product thoroughly before I took a mass of it to do my percent yield, because if there was any water in there, that mass is not what I'm supposed to be reading. I just want to know how much the aspirin weighed. So again, percent yield's not supposed to be over 100%. If they are, it's because you weren't paying attention to something else that might also be there. 73% also really isn't a bad percent yield in context of chemical reactions. Usually, just like your grades, it'd be beneficial here to have something over 70, but this is actually good. I wouldn't say that a D on a test is very good, but in the world of chemical reactions, anytime you get over 50% yield, that's usually a pretty good yield. It's pretty rare to get 100%, right? Anywhere in the 90s is really, really good. Right? Just like an A is really, really good on a test. But it's all relative to the context. Some reactions are easier than others to go through to completion. Some you'll have a very, very low percent yield for. So it just depends on what reaction it is as to whether that'd be good or not. Okay, so that covers the percent yields. That covers this whole section.